Hello, geometers and general seekers of truth. Welcome to the lesson on inscribed angles and polygons. So let's start with our first two definitions. An inscribed angle is an angle whose vertex is on the circle. So let's say you have a circle. We have a circle here. Let's call this, give it a center called Q. Okay. Now we've seen central angles before. The word inscribed means that the vertex is on the circle. In other words, it is touching the circle itself. So if I have something like this red angle here is an angle. Well, let's name it ABC. So in this case, angle ABC is an inscribed angle of circle Q. Angle ABC is an inscribed angle of circle Q. Now, the arc that lies in the interior of the inscribed angle and has endpoints on the angle is called the intercepted arc. Okay? So this terminology is not meant to be tricky for you to understand. So the arc that is here, that I'm highlighting here, from A to C there in yellow, that's called the intercepted arc. In other words, the arc that's cut by the angle. So arc AC, and by default, remember this is a minor arc, is the intercepted arc of angle ABC. So the angle here that's on the circle, that's called the inscribed angle, and the arc that it cuts or that it intercepts is called the intercepted arc. And so with this terminology down, with this vocabulary, we can move on to some very useful theorems here. Theorem 10.7, the measure of an inscribed angle. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. So in other words, looking at this picture up here, we're using the picture above. Okay, the measure of angle ABC, that's the inscribed angle here, is equal to 1/2 the measure of its intercepted arc. So 1/2 the measure of arc AC. Now keep in mind though that arc AC is really angle AQC, okay? Because from what we've learned before, the measure of an arc is just the measure of its central angle. So another way we can say this is that the measure of angle ABC is equal to 1/2 the measure of angle AQC. And of course, there's many ways, there's other ways we can rewrite this too. So we can say 2 times the measure of angle ABC is equal to the measure of arc AC, or 2 times the measure of ABC is equal to the measure of angle AQC. So these are 4 different ways of saying the exact same thing. Okay. Now we are going to prove this theorem because it is a fairly significant one, and it's something that we're going to use to prove a bunch of other theorems as well. Alright, so we're all set up here to do our proof, and I've just redrawn the picture here, and we are going to show that the measure of angle ABC is exactly equal to 1/2 of the measure of angle AQC. And the proof idea here, it's important to remember these little ideas that we use in these proofs. We are going to make some isosceles triangles using the radii. Okay? So this is one trick or one technique that you should practice and refine, is that when we're doing a proof of something that involves a circle, we should take advantage of the fact that there's that all of the radii in the circle are equal to each other. So I'm going to start with that. So I know that AQ and BQ must be congruent to each other because they are radii. and I can put in some angle measures here. So let's call this angle x. We don't know what it is, but let's call it x. Now, if this angle is x, then this angle up here is also equal to x. Okay, so this is I'll put it this way, the measure of angle QBA is equal to the measure of angle QAB. And this is the base angles theorem. Now I'm going to do a similar thing with another radii. So I'm going to take a radii and connect it between Q and C. And once again, QB is congruent to QC, so that these two angles here must be congruent to each other. Now we have to be careful. We don't want to label these angles x. We know that these two angles are congruent to each other, but they are not necessarily congruent to the angles of the other isosceles triangle. So we have to label these y. So we can say the same thing, that the same thing is here. The measure of angle QBC is congruent to the measure of angle QCB. Measure of QBC is congruent to the measure of, it's QBC is congruent to, I'll put measure to be consistent with what I have. Measure of QBC is equal to the measure of QCB. Okay. Once again, base angles. Now, it may seem to you like we're going nowhere with this, but rest assured there is an end to this proof. So now if you look at this, we have that the measure of angle ABC is equal to x plus y. So we want to show that the measure of angle AQC, what we're going to show now, is that this angle here is going to be equal to 2x plus 2y. So now we show that this angle here is equal to 2x plus 2y. So now how are we going to do that? Well, the approach is an old one, but a good one. So if this angle is y and this angle is y, then that means this angle in here, we say that the measure of BQC must then be equal to 180 minus 2y. My marker is dying out here. Let me get a new one. Okay. BQC, that angle right there, must be equal to 180 minus 2y. And the reason is the triangle sum theorem. And similarly, over here, this angle right here, part of triangle ABQ, must be equal to 180 minus 2x. Okay, so that's the measure of angle BQA is equal to 180 minus 2x. So now if we look at these three angles, BQA, BQC, and CQA, so these three right here, together, they must equal 180 degrees. Okay. So let's see. 360 degrees, because these three angles right here form the full circle. The three of them added up together, their arcs, make up the full circle, so they must equal 360 degrees. So what do we have? We have 180 minus 2x plus 180 minus 2y plus the measure of this angle here, which is AQC, must be equal to 360 degrees. Okay. And now we do a little bit of algebra. So on the left side here we have 180 and 180, so that's 360 degrees, minus 2x minus 2y, okay, plus the measure of AQC is equal to 360. So what that means is we can subtract 360 from both sides, and we get negative 2x minus 2y plus measure of AQC is equal to 0, since we subtracted 360 here. Now we can add 2x and 2y to both sides, and we get the measure of AQC is equal to 2x plus 2y. Then we are almost done. Remember what we were trying to show. Sometimes these proofs get long and lengthy and we forget what we're trying to show. But we have angle ABC here is equal to x plus y. We want to show that AQC is going to be equal to 2x plus y. And we have just that. The measure of AQC is equal to 2, and we just factor out x plus y. And this is the distributive property here. But wait a minute, x plus y is equal to the measure of ABC. So we do a little bit of substitution. And that completes the proof. Well, you can go one step further if you'd like and multiply both sides by 1/2. And we have the exact form that we're looking for. Okay. Now, this proof is really lengthy, but I want to show you, kind of a big picture of this. What did we really do? We made some isosceles triangles with these radii, and then label these angles something, x and y, and we're not even solving for this. We're just working through and just using variables to represent this. And just by using those variables, we can demonstrate that, well, this angle here, ABC, is equal to x plus y. And then we're looking at the circle, and the rest of the stuff in green here is just algebra that shows that AQC must be equal to 2 times x plus y, or 2 times the measure of ABC. Okay, so there you have it. We have completed Theorem 10.7. And now we return to one more theorem here in this video that says if two inscribed angles of a circle intercept the same arcs, then the angles are congruent. So let me show you what this theorem says. So let's say I have an angle here that intercepts arc AB. Okay, let's call this angle D. Right. And I have another angle over here, let's call it F, that also intersects arc AB. Okay. So what that says then is that then the measure of angle ADB, it's a D, ADB, so this blue one must be equal to the measure of angle AFB. Okay. So two inscribed angles intercepting the same arc, they have to be equal to each other. This proof I am going to ask you to try on your own. And a brief hint, use Theorem 10.7 to help you. Okay. Don't try to do this proof some new way, just use an existing theorem to help you. And in fact, Theorem 10.7 is going to be very useful as we work through some of these other proofs and some of the problems on the next section here.